We're going to get started. Our first speaker this afternoon is Benoit Chenot. He's going to talk to us about what Python can learn from Erlang. Please welcome him.
Thank you. Okay. Yes. So I'm here to speak about what Python can learn from Erlang. So I'm pretty excited to speak about that, my two preferred languages. So quickly introducing myself, I'm the Genicon author. I'm doing a lot of Python and Erlang codes on C code and whatever. I'm doing open source for livings and doing some consultings. So what Python can learn from Erlang? At first it can be understood as a joke. Python and Erlang, some buzzwords. Erlang is about message passing. It's about concurrency. It's about being able to launch multi-process at the same time. Python is one thread, an object-oriented language, where Erlang is a functional-oriented language. But according to Alan Key, object-oriented programming is not what we know in Python. Object-oriented programming is about message passing. It's about hiding the states to do the final user to the code. It's not about having a representation as an object like we show in Java, in Python, in C++, or whatever. It's about passing message, changing properties to a state, but hiding everything inside objects. So maybe, in fact, in Erlang we are doing objects without doing objects programming. And in Python, we are just doing a Python objects. But my talk is not about trying to reproduce what we do in Erlang in Python. It's about reliability. And because this is not about performance, this is not about making your program more performant because we will apply some patterns of Erlang. Performance is just a side detail of the reliability. If your program is not reliable, it won't perform. How it could be performing if your program is crashing every time. You need to have a program reliable first, then you can make performance. And you won't probably use your language to have performance. You will do that in C or do that by changing the algorithm, etc. But this is just a detail. You have to have a reliable program first. So what's a reliable program? This is a program that is resistant to the failure. Enough resistant to the failure, at least, to recover easily. Because your program will fail. You can have many unit tests. You can have many load tests, etc. But trust me, believe me, your program will crash. You can invest whatever you want in test, your program will crash. So you need to be able to recover easily. And being reliable also is being able to have your service online, even if you're upgrading your code, even if you're fixing an issue. And having a real program needs to have a way to do upgrades. In fact, the problem is simple. We need to have a program that is that stay alive, at least enough times to be able to store its state and being able to recover easily. Because your data programming is about having input and output. And when your program crash, at some point you had some data in your programs. If you're working with a bank system and your bank system is crashing at the moment you were making a transaction, maybe the transaction will be passed and the bank will have recorded that your transaction is gone and you have some $1,000 or euros less in your account. But you didn't get the money. So if your program didn't add the time to store its states, to recover from the last state, it won't know, and your bank will have less euros on it, but you won't have the money. Then you're screwed. You need to be able to stay alive enough times. In Erlang, it's done by process isolations and pattern matching, which are just assertion, as we will see, and message passings. And no shared memory. In fact, process isolation is about that. So we have here 4 processes running and talking to each other. Each process are isolated. They are not sharing anything they are span in their world. They know only about their data. They don't know about each other. The only way they are knowing it to each other is by passing message to them, to each other. So it allows that. So when a process crash, and at some point you will have a process that crash, your system continues to operate. Because every process is isolated, the process will continue to run. And the system should be able to detect the failure and relaunch it. And in Erlang, this is quite easily done by using supervisors. When the process crash and you supervise it, the supervisor will detect that the process crashed and will relaunch it. But in Python, this is not easy to do. So generally, what we are doing, we have our stacks of reliability of high availability stacks. So we have supervisors, which can be supervisor D or system D or whatever, that will be able to relaunch your programs. You have load balancer to be able to reroute the traffic when one of the machine crashed. You have containers, so you can eventually do auto upgrade. If you're using Docker or Rocket or LXD, you are able to say, I'm upgrading my code, I'm launching a new container that will override that one. And at that time, I'm using my load balancer to balance the traffic. So we are doing that by using the systems. But you may have supervisors. Supervisors are just restarting your programs. If you restart your programs without knowing your latest state, you will start from scratch. You won't be able to know where you stopped. And sometimes it can cause issues. So you need to program in a conservative manner, even in Python, so you will be able to store your states at some point. And yes, indeed, process isolation is hard or quite impossible, or at least without changing a lot the runtime. Because everything is running in one thread. Even asyncio is running in one thread, even G11 and the greenlet, or the fibers all are running in one process. And running in one process, in the same threads. And because of the GIL, everything is locked by the main thread at some points. And everything is sharing some states, everything is sharing some memory. So if you have a thread that is crashing, it can impact all other threads. You don't have any real process isolation in Python. In fact, the only way to have it is to use OS processes. So you can do it using multiprocessing or using the JUnicorn engine. And this is what we are doing in JUnicorn. We are spanning process. Each process don't know about each other. They are running, they are handling all the requests coming to the processes. And you have the main processes that is doing some arbitration, supervising every process, restarting every process if they crash, or stopping if a process was too long to answer. Stuff like it. So you can do process isolation in Python using OS processes, but it's quite hard. There are some other projects that are working on it. There is PyParallel, which is mostly working right now on Windows. That allows your code to run in parallel. So threads are really real threads running in parallel without knowing it to each other. It's also unlocking some call to I/O, like sockets or files. So it started to work quite good in January, and maybe it would be a good step, the next step of Python. At least this is a core fork of Python, and it's on Bitbucket. The other thing is PyPySTM. Maybe it will go somewhere, but with PyPySTM, so you are able to launch real processes. You won't change anything in the syntax in the language, and you will be able to maybe isolate process in Python. But for now, you can't do that. So, but we can still do some stuff in Python. We can let it crash. And by let it crash, we mean your program should fail fast. It should fail fast because if it fails fast, you will be able to recover it fast, and you will have a better availability. You need to crash early. Don't catch too much. Don't try to catch everything in your programs, or at least catch it try and accept, and re-raise the exception and let your program crash. Let the supervisor later. Just crash the time to store your state or log everything. Yes, you need to crash in a way to recover fast. One principle to follow for that is to make most of the code immutable. By immutable, we mean that any input will always get the same output, and you will be able to replace the function you use by the results and continue with other functions without changing the output. By checking, so for example, when r equal 1, r should be always equal 1. It shouldn't change the value. You shouldn't change the value later. It's easier to think about that. If your value don't change, this is like math. If your value don't change, then you can share it with any processes because it's static. So you can copy it to another process. It won't change the value. Your value is static, and you get a snapshot of it. It's easy to test because you know the value because the value doesn't change. It's easier to test, and it's quite safe because the value doesn't change. You don't have to look to make sure that you can override the value. You just use one variable at a time. Of course, the real world is mutable. Today I have no air. Yesterday I have air. And if I have made an object, a value on me, the only thing that didn't change in that is my identity. I'm still Benoît Chenot. And my identity doesn't change, but the properties attached to my identity change. But they are changing at one point in the time. So at some point, you can have snapshots of your data, and you can store them like a state. To give an example in Python, so you have a person class in which we record the occupation and the age. So we have one developer which at some point is a student, and we record that. And at another point, we store a new occupation and a new age. Of course, you need to have a way to refer to the developer at some point. So we record the identity in a hash, in a dict. And the identity is dev1 and devn, etc., with the objects at some points. But the dictionary should be immutable too, because you all have this issue sometimes at some points. When you iterate the dictionary and try to update it at some point, then you won't have the latest value, and you can also run in recursive loops, etc. So you also need immutable data structure. And you have many libraries that could help you for that. So you have Functon. I won't give any example about that, but Functon gives you a lot of data structure and some functional helpers that you can use in your code, making all your variable immutable, making some function immutable, always returning the same value, for example, whatever the state. You have frozen dictionary, hash. So you can, when you update a hash, it gives you a new, when you update a dictionary, it gives you a new dictionary instead of giving the same instance, which means that you can have a snapshot of your dictionary and pass it to any other processes or thread or any part of the code at some point. You have PyStance, which is like Functon. I dislike a little PyStance because it considers that an immutable data is frozen, where an immutable data is not frozen. It's just immutable at some point. It's just frozen at some points. You're still updating an immutable data. It just returns a new instant, a new data. And PyStance doesn't allow that. One of library I quite like is FunctionPy, which is quite new. I think the initial release was in October last year. And it gives you a lot of helpers and a lot of data structure, immutable data structure that you can use, and it's pretty nice. We need more. I'm still surprised that we don't have any immutable data structures in Python standard library. We should have that. We have some immutable data, but we don't have them in the standard library. And having some immutable data structure in the standard library would allow any developer to use them rather than continuing to use dynamic data structures that are very dangerous at some point. Because you can't store the state or you can't share them easily. So it was about immutability. The other way to make your code reliable is don't be too catchy. Don't try. Try to fail fast. Do not cache everything. I see a lot of Python code that are trying to catch everything inside try except loops or with finally too. So they are trying catching at any point. And sometimes you have a lot of exceptions handled inside other exception handlings, etc., in loopings. And the developer is trying to catch every case he has in the code. He's trying to have an answer for every case. Don't do that. Just let crash your program. Try catch less. Just catch what you really want to log, or just catch at some point where you can store states for your program. It can be early, and possibly it should be early in your programs. Try to when your socket fails, for example, just let it fail, and then you will restart. If you need to store at this point what you were doing, then try store your state in Redis, in cache, in file system, or whatever, and re-raise your exception. Just let your program crash and let the supervisor restart it. The other way also is don't try to put exception anywhere, in any place. Try also pattern matching. Pattern matching in Erlang is like that. So if you see the first line, we are trying to connect a socket to a remote, and generally we expect to have a tuple OK socket. If we don't have this tuple, if we don't have the what we expected, we will just crash. Because if we can't connect, then connect will return error on an error tuple. But we don't try to catch or to understand if we need to reconnect, etc. If we need to reconnect, then we try to match the error case or the OK case and do what we want. But in main case, generally, you just crash. I'm just saying, okay, I should have OK socket. If I don't have OK socket, my process will crash, and it will be restarted. Same for message pacings. And you can see a pretty interesting thing with that is we are able to separate the decision from the actions here. We are receiving a message that they may say the message, and we say the message somewhere else, maybe in another process, maybe on another machine. This is what you should do. Pattern matching in Python could be done with this nice function, this nice library. So you can do pattern matching on functions. You can accept arbitrary arguments, and then you can assert the argument test, which arguments you have in your functions, and do the appropriate case. And finally, you should separate most of the time the action from the decisions. For example, here we are doing a class actions, and we are inheriting from it. We have a class send message and class logs, and we try to send the message. Generally, when you send the message, you send the message. You handle everything in the same functions. Here we just create new action. We create an action send message. We create an action logs. And then we have a run function somewhere. Could be done serially, it could be done using a fiber, it could be done in an asyncio chain, or in a Yelp chain, sorry. And we iterate over the action, and we do the action. The interest of that is that you can have an OS process, or an application doing the send message and the logs, and maybe with ZMQ, you are sending this message to another process or to another machine that will do the real action. And then you can do your own clustering or your own scheduling things if you want to. And that's all. If you have any question.
Thank you. So if there are any questions, you can use the microphone next to the camera, please.
Somebody?
Hi, great talk. I was just wondering, what is the library for the pattern matching thing? I just didn't hear the name. I'm very interested in it.
Sorry?
The library you use to do pattern matching in Python
Yes.
with the decorator.
Patterns?
Okay. Okay, great. That's all I wanted to know.
Okay.
Thanks.
Anything else? No. Okay. Okay, thank you.